Hello, and thank you for joining us. Today's webinar topic is Do It Right, TOC Determination by US EPA Method 415.3. Our presenter is Steve Proffitt, Applications Chemist for Teledyne Labs. If you have any questions, please feel free to submit them throughout the presentation or email Steve directly, and he will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Steve Proffitt.
Hello, and thank you for joining me for this presentation on total organic carbon determination by US EPA Method 415.3. We're going to show you how to do it right and make it easy. My name is Steve Proffitt. I'm an applications chemist with Teledyne Labs in Mason, Ohio, specializing in product marketing and method development. Okay, at Teledyne Labs, several divisions are consolidated: CTAC, Tecmar, ISCO, Hansen, and Lehman Labs for instrumentation essential for diffusion, elemental analysis, physical testing, pumping, automated liquid handling, GC sample prep, chromatography, dissolution, and evaporation requirements. So there's a lot that we do at Teledyne Labs. And Teledyne Labs enhances the visibility of our products, brands, and services, aiding customers in finding viable solutions that meet their current and future needs. The agenda for the presentation starts with a brief introduction of the US EPA and its origin. Next will be a TOC overview. Then we'll look at the approved methodologies for 415.3 and the analyzers we have at Teledyne Labs that meet the requirements outlined in the method. Next is a demonstration of TOC determination in surface water samples from different sources. Then I'll wrap it up with highlighting the features and benefits of choosing a TOC analyzer from Teledyne Labs. The official name of the method, 415.3, is determination of total organic carbon and specific UV absorbance at 254 nanometers in source and drinking water, revision 1.2. Let's start with a brief history of the origin of the US EPA and how and why they're involved in creating and publishing analytical methods. Beginning in the late 1950s, environmental conservation was becoming a widely discussed topic in the United States. Concern about air and water pollution heightened in the 60s, steadily increasing as numerous disastrous events were occurring across the country. Oil rig accidents, foul beaches, a heavily contaminated river in northern Ohio spontaneously burst into flames. Waste was being dumped unregulated into the Great Lakes. Occurrences such as these were becoming increasingly widespread. Public outcry for pollution regulation prompted action from the United States government. In early 1970, President Richard Nixon presented his plan for protecting human health and the environment. By the end of the year, the proposal was approved, and the United States Environmental Protection Agency was established. So a lot of people don't realize they've only been around since 1970. But that's, and they were able to go back to like standard methods that had been around since the early 1900s to help with the methodology and the regulations. One of the many tasks of the EPA was to create regulations, guidelines, and methods for monitoring and controlling environmental pollutants. And of the numerous methods established, Method 415.3 is the US EPA sanctioned method for quantifying levels of TOC in water. TOC analysis is a broad, non-specific measurement of organic carbon. Organic carbon in a water sample can be comprised of carbon-based pollutants, including volatile and semi-volatile organics, oils and greases, bacteria, living microorganisms, and decaying matter. Total carbon in water also contains inorganic carbon, or IC, which can be cyanides, elemental carbon, dissolved CO2, carbonates, and bicarbonates. To get a TOC result, the analyzer must specify between TOC and IC. Later, I'll explain the methodology used to remove IC from the sample to get the final TOC result. Regulatory agencies such as the EPA and state-level safety and health administrations have established TOC limits in drinking water, source water, wastewater, and sewage treatment effluent. These regulatory limits serve to maintain a level of cleanliness in these water types to help prevent harmful consequences to health and the environment. In TOC determination, organic carbon in the water is oxidized to produce CO2, which is then measured by an infrared detection system. As stated in method 415.3, there are two different approved approaches for the oxidation of organic carbon in water samples. The first one is combustion in an oxidizing gas, and then there's UV promoted or heat catalyzed chemical oxidation with a Persulfate solution. Teledyne Labs offers products for both methodologies. First, I'll talk about combustion in an oxidizing gas. This method is suitable for samples with a higher level of TOC and works well with organic compounds that are hard to chemically oxidize. And Teledyne Labs offers two TOC analyzers that use combustion oxidation. We have the torch and the Lodex. So for the combustion methodology to achieve a TOC result, the inorganic carbon fraction of the sample must be removed. On the right here, we've got a picture of the front of the instrument inside the tinted shield once you open that door. On the right is the IC sparger. So IC removal occurs automatically inside the IC sparger. This is the torch unit. The Lodex is set up very similar. So over here is the acid vial. You can use a 40 ml vial or a 125 ml vial for holding your acid reagent. It's added to the IC sparger through the syringe and the multi-port valve. The acidified sample in the IC sparger is then sparged for a predetermined time, releasing the IC from the sample out a vent out of the back of the instrument. After IC removal, an aliquot of sample is injected into a combustion tube containing platinum catalyst at a high temperature. And our tube is inside a furnace that opens up. It's what we call a clamshell design that will open up and give you easy access for combustion tube maintenance. Once the carbon in the sample is converted to CO2, then is swept into the NDIR detector for the TOC result. The UV persulfate oxidation method is suitable for samples with lower levels of TOC. The analyzer combines ultra-low instrument background with larger sample volumes along with patented detection technology to deliver lower detection limits. Generally, these samples are cleaner in nature, ranging from surface waters to water treatment facilities to purified waters for pharmaceutical production. To achieve a TOC result using the fusion, like with the torch or Lodex, the IC fraction of the sample must be removed. Again, IC removal occurs automatically inside the IC sparger here on the right. The acid is added to the IC sparger along with the sample. The acidified sample is then sparged, removing the IC from the sample. After IC removal, an aliquot of the sample is transferred to the UV reactor, where you have your UV lamp, and with the UV light, in addition to sodium persulfate along with sparging, the carbon is oxidized into CO2 and then swept into the detector. So the US EPA has several requirements to ensure that an analyzer can be validated to perform method 415.3. First, you have your initial demonstration of capability, where you must prove that you have a low system background, you have low carryover, which is verified by running a reagent water after your highest calibration point. Accuracy, for example, on a 5 ppm standard must be plus or minus 20% of the true value. Detection limit determination less than 0.35 ppm carbon. Your instrument calibration verification, your R-squared value must be greater than 0.993. Most labs will even adapt a better linearity fit of 0.999. And then IC removal efficiency, whatever you've determined your method reporting limit, the IC removal efficiency, you must get down to less than half of that value. And that will be determined according to what method or calibration range individuals are using. And then for precision, for example, a 5 ppm carbon must be less than 20% RSD, which most people actually go to probably like a 10%. And along with the initial demonstration of capability, independent quality control samples must be run and validate the operation of the system. For a schedule, you have to run continuing calibration checks to make sure the calibration is still valid. You'll run laboratory reagent blanks, laboratory fortified matrix, which are spiked samples, your matrix spikes, and field duplicates. So while Teledyne Labs TOC analyzers easily pass the IDC requirements, the demonstration presented today will focus on guidelines and requirements commonly established using US EPA Method 415.3 for analyzing a set of environmental samples. This table represents acceptance criteria that is derived from requirements and guidelines within US EPA 415.3 and regularly used by environmental laboratories. Like I said, most people will go with a 0.999 initial calibration, R-squared value, and reproducibility of replicates. You're going to want them to be less than 10% RSD. Initial calibration verification, plus or minus 10% of expected concentration, as well as the continuing calibration checks, which continuing checks will be run after every 10 samples and at the end of the schedule. And there'll be duplicate samples, which you want your relative percent difference to be less than 20%. Matrix spike, plus or minus 20% of the expected value, then the matrix spike dupe, which is a combination of dupes and matrix spikes. So several sources of surface water were individually collected in 40 ml sample vials and analyzed on both the Fusion and the Torch. Comparative results from each instrument will be analyzed for accuracy equivalent to duplicate sample acceptance criteria to see how well the instruments the results line up between one methodology or to the next. On the left, there's the water inlet for Cincinnati Water Works on the Ohio River, where some samples were collected. And over on the right is the inlet at the William H. Harsha Lake for West Clermont County, Ohio Water Works. Other sources collected include Northern Kentucky Water Works inlet on the Ohio River, and a couple of other local sources, the Little Miami River near Newtown, Ohio, and the East Fork Little Miami River in Milford, Ohio. The water samples were collected, preserved, and stored according to guidelines in Method 415.3. The samples were collected by this guy. That's actually my son. He was pretty excited about this. Anyway, samples were stored at less than 6 degrees. They were collected in pre-acidified vials to achieve a pH of less than 2. And samples were analyzed within 28 days from time of collection. And all those requirements have to be followed. If not, the samples cannot be used in compliance with the Safe Drinking Water Act established by the EPA. For both the Fusion and the torch, many method parameters are adjustable to modify the methods for particular sample types and concentration ranges. For this study, the methods used are detailed here. So for the Fusion method on the left, I used a sample volume of 6 milliliters that obviously is adjustable, and then that will give you your optimal sample range as that's changed. If you put in more sample, you've got a lower optimal range. So for this this method, I can go up to go up to 10 ppm. You can add a dilution factor. I've gone with no dilutions. Acid volume, as well as, if you look down here, I see sparge time. If you've got high inorganic carbon containing samples, acid volume and sparge time can be increased to improve the efficiency of the IC removal. You've got other things like reagent volume, a reactor pre-rinse, detector sweep flow, pre-sparge time, and the system flow for flushing everything through to the detector. Now on the right, for the torch method, you use less sample volume for the combustion type of methodology. On this one, I've used 0.7 milliliters to create a range up to 30 is what it says in the optimal range, but in a lot of cases you can go higher than that. You just do not want to max out the upper end of the detector. So what I did, we'll see later, is I actually ran this method up to a 100 ppm range. Now you've got a water chase volume, which if you, typically with the combustion unit, you're going to have dirtier samples, so you can chase the sample through with water to make sure you're getting everything into the combustion tube and getting a true representation of what the sample is. And again, there's a dilution volume. You can do injection line rinses. You've got the acid volume, IC sparge time, a lot of parameters that are the same as with the Fusion. So to calibrate the analyzers, a 1000 ppm organic carbon stock solution was prepared by dissolving 2.125 grams of potassium hydrogen phthalate, or KHP, and 1 liter of reagent water. From this stock solution, working calibration standards were prepared. The working calibration standards for each instrument are the high concentration calibration points for each curve. The additional points for each calibration were made through the auto calibration feature, in which the working standard is used to make other points in the calibration curve by automated serial dilutions. So through the syringe pumper, in the dilution, it can take from the one standard, create all the points for a calibration automatically. And just to look at the calibrations that were achieved, on the Fusion, I went from 0 to 20 ppm. You can see the linearity is almost perfect. I've got a 0.99951 R² value. And then on the Torch, like I said before, I went from 0 to 100 ppm. Again, really, really good linearity at 0.99964. To demonstrate the accuracy and precision of the Torch and the Fusion, calibration points and check standards were analyzed in triplicate. The precision of each instrument, as you'll see in the results, is indicated by low percent relative standard deviation for each triplicate analysis. Accuracy is demonstrated by excellent percent recoveries for the check standards and matrix spikes, as will be seen next. Here's the results from the Fusion instrument. So looking at the initial calibration verification, the percent recoveries are very accurate at 105 and 103%, and the RSDs are less than 1% RSDs, which indicates very, very good precision. Our samples are run next, where we've got Ohio River, Cincinnati, Northern Kentucky, East Fork, Little Miami River, East Fork Lake. So looking at these TOC values, they're all actually very, very clean source waters for the area. And when we look at the dupes, the instrument shows how accurate and precise it is with the low percent RSDs, and the relative percent difference is only 0.13 for the matrix spike and matrix spike dupe. Very low percent difference, and all these recoveries right around 100%. The results for the Torch show similar exceptional accuracy and precision, as well as an outstanding replication of the duplicate samples. Again, looking at the percent recoveries of the initial calibration and verification, right at 100%. Low percent RSD. Percent differences look really good across the entire range of the samples. Percent recoveries right around 95, 90%, which is very good. So this is the comparison of the instruments, the Fusion versus the Torch. And they, again, the results show very similar results. The percent differences from Fusion to Torch result on all of the samples taken percent differences are very good, all below 10%. However, the one from the Little Miami River, that one I remember had a cloudy, more particulates in the sample. So the percent difference is just outside of the 20% acceptance limit, but that's probably a result of, more than likely, I'd say it is a result of the particulates within the sample being oxidized by the combustion analyzer, whereas the fusion will not oxidize particulates as efficiently. So in a lot of cases, you are with these waters, you'll filter the water through a 45 micron filter to get what's called a dissolved organic carbon result. And that's similar to the TOC, but that's just with removing the particulates. So in conclusion, regardless of oxidation methodology, Teledyne Labs offers instrumentation that will consistently deliver precise and accurate TOC measurements. The Fusion UV Persulfate TOC analyzer on the left, and then the two combustion units, the Torch and the Lodix. The Fusion UV Persulfate analyzer is an exceptional analytical instrument for TOC determination by method 415.3. Its integrated auto sampler provides a small footprint for maximizing laboratory bench space. As you can see on top of the instrument here, that's your auto sampler, which is a carousel that will rotate around, and then you have your robotic arm that will move out and up and down to sample the vials. In the center position, that's where your standards will be. So if you're making a calibration up to 10 ppm, one of those is going to be 10 ppm, and then the automated auto calibration will make your calibration from the one standard. And it also features a static pressure concentration detector, which enables superior detection limits for analyzing low-level concentrations. Benefits and features of the Fusion include an advanced syringe multi-port valve fluid management system and a robust built-in auto sampler with the ability to build automated calibration curves from one standard, as I've mentioned. Should a sample exceed the calibrated range, the Fusion can utilize a feature called IntelliDilution, which will dilute the sample to within the calibration range without interrupting the sample. And then the TOC TechLink is the fully automated, optimized user interface that simplifies operating and maintaining the Fusion. Within the software, there are pre-developed methods that allow for quick startup, and there are variable parameters within the methods that I went over that will permit for method development and analyzing end characteristic samples. The Fusion is truly an excellent choice for determining TOC levels in surface waters used as source water for water treatment facilities. So the Torch Combustion Oxidation TOC analyzer again, this instrument meets the guidelines and requirements for US EPA Method 415.3. The standard built-in auto sampler, same as with the Fusion. It has a tray with 75 positions to accommodate the standard 40 ml sample vial sizes. Other tray sizes are available, as well as a tray with a stirring mechanism for samples with particulates or suspended solids. Same thing. The torch is equipped with all the features of the Fusion that were detailed earlier: auto calibration from one standard, and teledilution, and TechLink with pre-developed methods. Additionally, the torch has the sensitivity to analyze source water and drinking water samples, and the analytical range to monitor wastewater samples. The Lodix is our lower cost combustion TOC analyzer that can also be used for US EPA Method 415.3. Its pressurized fluids management system eliminates the costly syringe drive and multi-port valve to provide an economical price to fit any laboratory's budget. The flow-through NDIR detector enables faster throughput of samples with a 15-minute average runtime for triplicate analysis. Teledyne Labs is the obvious choice for analytical instrumentation. Excellent choices are offered for the particular methodology required for US EPA Method 415.3. For UV persulfate oxidation, the Fusion is an industry standard for source water, drinking water, and pharmaceutical sample analysis. For combustion oxidation TOC, the torch is loaded with features such as auto calibration and teledilution. And the Lodix, which provides fast run times, an economical price point, and low maintenance, reducing downtime and costs. Teledyne Labs is superior in all areas: built-in robust automation, a fully optimized user interface, outstanding analytical performance, and unsurpassed applications, technical, and service support. Through Facebook, X, LinkedIn, and YouTube, it's easy to connect with Teledyne Labs to stay up to date with our latest innovations and applications. Also, be sure to visit our website at teledynelabs.com. Thanks for the opportunity to share this information. My name is Steve Profit, and I welcome any questions anyone may have. Please contact me at steven.profit@teledyne.com for further information. Thanks again, and goodbye.